All right, now we're going to talk about a very specific sort of series. It's called the alternating series. Alternating series here. An alternating series is of one of these two forms, either a 5.13 or 5.14. So basically, your main thing is it's going to oscillate between a negative and a positive. So the first form here, we take the sum as n equals 1 of a negative number raised to the n plus 1. So when we put in the first one, 1 for n, it'll be 2. So that means our value will be positive. So we've got this bn, just some nth term or whatever that we're going to have, some value that's going to go up as we increase n, some series evaluated to n. So the very first value will be positive. The second value will be negative, illustrated by this negative point here, and then they'll oscillate between a positive and a negative and so forth. And we've got a specification down here that our b of n can't be less than 0. Otherwise, it doesn't make a lot of sense. If we determine that it's negative, then we can just shift it down to this 5.14, where instead we start with 1 for n, and negative 1 to an odd number is going to be negative, negative 1 to an even number is going to be positive. So we get a negative, then a positive, then a negative, then a positive, and so forth. And again, if you're in a situation where your bn is negative, then you just pull out an extra negative 1 and alter your series to either be, if it was n raised to the n, you raise it to the n plus 1. If it was n plus 1, you can just change it to the n. That'll be fine. All right, so that's what an alternating series is, and so as an example of that, we can look at so n equals 1 to infinity of 1 over n. Let's see, negative 1 to the n, 1 over n. So this equals, when n is 1, we put in a negative, and so that'll be negative 1 over 1. That'll be plus 1 over 2, minus 1 over 3, plus 1 over 4, and so forth. So that's how that's going to work. Now, we have this test down below, this alternating series test. This theorem 5.13. So we've got the two different forms, whether our alternating series has we're raising the negative 1 to the n plus 1 or the n, whichever series we have will converge if both of these two criteria are met. Criteria number 1 is our new values. As n increases, whatever the value that we had for bn plus 1 is less than or equal to whatever we had for bn. So this has to be, so they have to be getting smaller. So if you look here, 1 over n, so the bn part is the 1 over n, so that goes from, goes from 1, the next one is 1/2, the next one is 1/3, the next one is 1/4, and so forth. Well, in this case, it is, in fact, getting smaller. So each subsequent bn plus 1 is smaller than the previous one, and if they're all equal, then that works too. And again, that's for all n greater than or equal to 1. And our second thing is also extremely important. The limit of the bn has to go to 0. So both of these things need to work in order for it to go to 0. So we test this limit. I did it again. Let's see. So limit as n approaches infinity of 1 over n, which would be our bn here for my example, equals, well, as the denominator gets huge, this goes to 0. So that by these two things, with this example, we note that n equals 1 to infinity, negative 1 to the n, 1 over n, converges. So it's going to converge by this alternating series test. Also, if it does not converge, then it's going to diverge. All right, there's really no option for this test not being useful. Now, you have to check this limit in order for it to work. So you take essentially the nth limit, but other than that, it's not a big deal. So part A, each of the following, we're going to determine whether or not the series converges or diverges. You don't just write converge or diverge. You have to actually do the sort of things that we did here. So let's do A. So first of all, part 1, we have, so in this case, our B of n is 1 over n squared. So if we look at our first one, so B1 equals 1 over 1 squared, which is 1. B2 is 1 over 2 squared, which is 1/4. B3 is 1 over 3 squared, which is 1 over 9th, and so forth. So what's happening? So we have all of these are greater than or equal to 0. So 1 over n plus 1 quantity squared will always be less than or equal to 1 over n squared. All right? So part 1 of this thing is going to work. Now let's check number 2. So we take the limit of the b to the n. So the b to the n here is 1 over n squared. And this equals 0. This equals 0 because as our denominator gets infinitely large, this is going to go to 1 over an infinite number, which is 0. We don't have anything on top disrupting anything, so we don't have to do any other checks, no L'Hopital, no nothing. So according to this, so this converges series converges by the alternating series test. Again, this doesn't work if it's not an alternating series. All right. This only works because, well, I mean, technically this one worked just fine. It's going to converge no matter what. But what about our 1 over n squared will converge? We know it's a p series. So note 1 over n squared is a p series with 2 greater than 1, strictly greater than 1. So just 1 over n squared, or the sum of 1 over n squared, will converge. But what about 1 over n? Well, 1 over n is a p series. That was our original example up here. 1 over n is a p series with n less than or equal to 1, which means that it diverges. So our alternating series above here converges, but our normal series diverges. And we'll get into absolute convergence versus conditional convergence later. And this was probably an example I'll reference then. It's a pretty good one. But this one will converge all the time, or will converge absolutely. Let's take a look at B. Let's do this in a different color here. So B, we have n over n plus 1. So we have this sum. That's -1. They had n plus 1 here, and then we're going to multiply this by n over n plus 1. So this part here is our Bn. All right, so as we go forward, we can test 1. So if we take for n equals 1, we have 1 over 2. N equals 3. We have, n equals 2. We have 2 over 3, n equals 3. We have 3 over 4. Well, what's happening here? They're not getting smaller. In fact, they're getting larger. And we know that, so they're getting larger. So it's failed the first part, so we're already messed up. So we don't have 1, so this is going to diverge. But we can also look at 2, the limit as n approaches infinity of n over n plus 1. We can use L'Hopital's rule, so this equals the limit as n approaches infinity of 1 over 1, which just equals 1, and that doesn't equal 0. So neither 1 nor 2 are satisfied. But we just need one of them to fail, and they just both happen to fail. So our series diverges.